Hello, my name is Michael Katz. I am a research staff member at IBM Research AI, and I will talk to you today about a joint work with my colleagues here on exploring context-free languages via planning, the case for automated machine learning. Automation of machine learning pipeline generation is a hot topic in AI, as the number of human experts data scientists is below industry demand. Further, the space of pipelines explored by human experts is a tiny portion of the entire the space of possible pipelines. Humans also tend to explore the same or very similar pipelines all over again, feeling more comfortable with what they are already familiar with. The automation allows to alleviate the dependence on human experts while generating pipelines of high accuracy. The history of automation attempts for machine learning pipeline generation is not too long. The most basic approaches were dealing with fixed structure pipeline for four steps, focusing on the data preparation, data cleaning, preprocessing, transformation, and feature selection, with a few choices of algorithms for each. The combined algorithm selection and their hyperparameter optimization problem was called cache. Recently, there was an attempt to apply HTN planning-based approach, allowing to move away from the fixed number of steps. However, it was not modeled in any of the existing HTN planning languages and used a dedicated solver for pipeline generation. Another line of work suggested to use genetic algorithms to explore the space of possible pipelines. The approach generated both valid and invalid pipelines and used regular grammars to prune the invalid ones. Yet another line of work suggested to use a Monte Carlo tree search instead of genetic algorithms, and again using regular grammars to prune the search. All these approaches further restricted their search space by allowing only chain-shaped pipelines. Our main contribution in this work is introducing a novel planning-based approach for exploring the space of possible valid pipelines. In order to do so, our solution uses a variety of existing planning tools. Going beyond what was allowed by previous approaches, we now allow for arbitrary dog-shaped data flow graphs. We define the space of valid machine learning pipelines with the use of regular grammars. We then define the corresponding HTML planning model with the space of solutions corresponding to the regular language. We used an existing tool to translate the HTML planning model to a classical planning model. Further, we can enrich the classical planning model by introducing user-defined constraints encoded with soft goals, and use an existing compilation to compile these soft goals away, obtaining again a classical planning model. We can then use planners that return a set of plans such as top K, top quality, or diverse planners to explore the space of plans, mapping each plan to a machine learning pipeline. Given a data science grammar, we transform it to HTML planning model, and then to classical planning model. We integrate user-defined constraints, turning the classical planning model to classical planning with soft goals, compile the soft goals away, obtaining again a classical planning model. We then use a top K planner to generate multiple plans, each post-processed into a machine learning pipeline. The pipelines are then trained on specific datasets, and their accuracy feedback is used to adapt the planning model. We start by introducing an example machine learning grammar. The grammar is an input to our system and can be easily modified. Among the terminal symbols, we have pipe operations, parallel independent execution, and concatenation of the output features. Grammars allow for rule-level control, for example, by specifying rules for a collection of possible algorithm hyperparameter values. Other terminal symbols of the grammar correspond to various algorithms and to their hyperparameter values. As a next step, the grammar is translated to an HTML planning and then to classical planning using an existing tool by Alfred et al. In order to focus the exploration of valid pipelines, we allow for specifying preferred non-terminal and terminal symbols. The non-terminal symbols correspond to the rules of the grammar and allow to prefer, for instance, using a particular family of algorithms. Choosing terminal symbols allows for preferring a specific algorithm or even a specific value for an upper parameter. The preferences are then translated to soft goals, which are added to the classical planning task. Then the soft goals are compiled away using the transformation proposed by Keder and Geffner, giving us again a classical planning task. The classical planning task is then solved with a top K planner, obtaining a large set of plans of low cost. Each plan is then transformed into a trainable pipeline. Given a dataset, each trainable pipeline is then trained on that dataset using an hyperparameter optimizer that can optimize over the non-specified hyperparameters. As a result of the training, accuracy scores on that dataset are obtained for each pipeline. A low accuracy score can be used as a feedback, adapting the planning model. In our current work, we adapted the model by changing action costs. That allowed to maintain the same plan space and change which subset now constitute a top K solution. Therefore, top K planners would find a different set of plans for a modified task in the next iteration. In order to investigate the practical feasibility of our approach, we performed an experimental evaluation. First, we checked if existing top K planners can be used for the classical planning tasks that are generated using our approach within the sensible time bound. For that, we generated a benchmark set from machine learning grammar, applying the transformation mentioned in the previous slides, randomly choosing constraint subset of sizes varying from 1 to 10, creating 10 tasks for each subset size. We ran a K-star planner on this task, requesting 4,000 plans for each task. For the tasks with up to 4 constraints, we were able to always find all requested plans in under 6 seconds. For up to 7 constraints in under 50 seconds, and for up to 10 constraints in under 500 seconds. As a typical human selection is around 3 or 4 constraints, we can conclude that the planner will not be a bottleneck to our approach. Moving on to the evaluation of the accuracy obtained by our approach, we tested our approach on 27 datasets from the OpenML collection. As on many of the datasets, all approaches obtain a very high accuracy quickly. We focus here on the 8 datasets for which no approach was able to produce accuracy larger than 95%. We compare to the handcrafted baselines of manually chosen by expert chains of lengths 2 and 3, with multiple possible algorithms to choose from for each node on the chain. We used hyperopt for optimizing the selection of algorithms for each node as well as algorithms hyperparameters. Our two approaches are one-shot generating 1000 plans and optimizing over the corresponding pipelines with hyperopt, and feedback, iteratively finding 40 plans, training with hyperopt, and using the obtained scores to modify the action costs for the next iteration. Our experiments show that changing the number of pipelines per round has limited effect on accuracy. In general, feedback accuracy is very close to one shot. We conjecture that our approach that penalizes algorithms that participate in pipelines of low accuracy is too simplistic to be able to guide the search towards pipelines of higher accuracy. Focusing now on one shot, in 5 of 8 datasets, one shot achieves the highest final accuracy among the tested approaches. There is only one case when the handcrafted tree ops eventually achieves a better accuracy, and 2 datasets where the final accuracy is eventually the same. We have introduced a novel application of planning to automating machine learning. Our application integrates multiple existing planning techniques, multiple problem transformations, and a solver that produces multiple plans. Further, we introduce a novel translation from grammars to HTML planning. Our application creates a planning model, generates plans, and then iteratively modifies the planning model based on previously produced plans to produce plans that better reflect user preferences. This allows, for the first time, to easily explore the space of possible valid pipelines without posing severe restrictions on the set of such pipelines. For future work, we intend to explore additional modifications to the classical planning model to account for the accuracy-based feedback. Additionally, we would like to apply a similar approach to other domains, such as natural language generation. We have made the PDL domain generated from the machine learning grammar publicly available. Further, many of the tools from our group are publicly available as well. Thank you. I can now take your questions.